Next speaker will be Wim Canning. He's from Delft University of Technology, Delft, the Netherlands. Please, the floor is yours.
Okay, good afternoon, ladies and gentlemen. Welcome to my presentation, which is entitled Effective Solutions to Deal with the Length Effect in Piping. My name is Wim Canning, and as the chairman said, I did this work while I was working at TU Delft. Last Monday I started working at Deltares. It was a small change. I want to thank my co-authors Timo Schwekendiek from Deltares and Professor Freiling from the Delft University of Technology. First, to give you a little bit of background about this paper, about this presentation. I just finished my PhD thesis, which is entitled The Weakest Link, Spatial Variability in the Piping Failure Mechanism of Dikes. This is a rather technical, statistical research, and since this whole conference is about flood risk management, I thought to give the subject a more management perspective and how can we effectively deal with situations that are unacceptable, which have a really high failure probability. So this is what this presentation will be about. First I will discuss a bit about this piping mechanism, about length effects, which was in the title. Second, about uncertainties, what are the dominant uncertainties in this piping mechanism, and which uncertainties may be reduced by doing measurements. In the end, I present a decision framework which discusses the trade-off between doing structural reinforcements to improve your structure or doing measurements in combination with some local reinforcements, and to see what is the most cost-effective, which I will evaluate on the basis of a few examples. Well, first, most of you I won't discuss extensively. This is the piping failure mechanism. Most of you know this failure mechanism. It's notorious all over the world. It was emphasized by the presentation of Mr. Link this morning about all the Missouri floodings. Well, basically what happens if there's usually we have especially in the Netherlands, but also in the US, we often have impermeable dike bodies and blanket layers on top of a permeable sand layer. Well, when the water level rises outside, there's usually water pressures start to develop. This causes uplift and cracking of this blanket layer, which results in a groundwater flow, and if the flow is strong enough, it carries along the sand, and the sand will be eroded away until the dike collapses. Yeah. Well, there's a few parameters that are important. First of all, of course, the head difference over the levee. But second of all, what is important for how quick the water flows when the erosion channel forms is the permeability. That's the main parameter there, and then the erosion resistance is mainly determined by the grain size, the D17. And well, all these parameters are highly variable, are stochastic variables. Well, and what we discuss here, usually we only look at cross sections. Well, now we usually have the problem that all these parameters, they fluctuate really rapidly in space. So if we take in the third dimension, there's rapid fluctuations of the resistance parameters. So what does this end up to? This is a highly schematized dike. Well, because of this rapid fluctuation of the resistance, we could say, well, that the resistances of individual dike reaches, these are independent while the loads are fully correlated. That gives you a simple series system, which can be modeled as this kind of system. Well, that's a really schematized version, just discrete elements. But I think for today's presentations, especially for doing measurements, this schematization works. Okay, there should be. Okay, some line disappeared. In reality, of course, okay, I will sketch the line with the pointer. In reality, of course, it's most of it is continuous. It's continuous fluctuation in space. So you get if you start evaluating your limit state function in the length direction of the dike, you get a fluctuating limit state function. In the end, what it all comes down to is the longer the dike, the more of these independent elements you have, the higher the probability of failure. Well, and this usually, at least in the Netherlands, it shows this often results, even though on a cross-section level things might be more or less okay, on a system level this results in unacceptable probabilities of failure. Okay, so well, like I said, we're going to look into this in this presentation into the trade-off between either doing measurements or just doing structural reinforcements. Before we can just say what the impact of measurements is, we have to know first what are the dominant uncertainties, and second of all, which uncertainties might be reducible by doing measurements. Well, I did some case studies in the Netherlands. I won't elaborate on them, but those of you who are familiar with reliability analysis know that if you can do reliability analysis with form, you get the form sensitivity coefficients, and they basically show you the contribution of each variable to the total probability of failure. Right. So this is what this pie chart is presenting. I use the Selmayr formula, which is used for safety assessments in the Netherlands. Well, I won't explain all the variables, but basically what it says is like the K, the permeability has like a high form sensitivity coefficient, the water level distribution, and the D70. So like the permeability, the D70, the grain size, and the water level, that are the main uncertainties that determine the total probability of failure. And that's also where we should look then for where efficient measurement strategies might be found. Now, second of all, this is only if we consider continuous fluctuation in the soil. We also have like this, I call it anomalies, like especially old riverbeds that are undetected, but are possibly there. I mean, they have a high impact on the total probability of system failure. So the exclusion of potential anomalies is also an important factor. We have to, so all these uncertainties, this is like all the parameters are assigned like mean values and standard deviations. Well, these standard deviations, they cover the uncertainty. But this uncertainty, it's consists of a lot of sources, right? So we can, if we have like soil uncertainties, we can basically make a distinction between either like inherent uncertainty that stems from the natural fluctuations in the soil, like either continuous variability or these anomalies. But the second part is we also have like a lot of modeling uncertainty. Yeah, so there could be like physical model uncertainty, could be measurement uncertainty, could be transformation uncertainty, and it could be statistical uncertainty. That's a rough distinguishment. Let's see, now there should be, yeah. If we do measurements, what do we actually reduce? So if we like measure like local permeability, if we measure D70, what do we reduce? Well, what we basically reduce is like this continuous variability and maybe a bit of statistical uncertainty. So that means that you only have like an option for effective measurements in case you have, in case your variability in case the uncertainty your parameter is mainly determined by like continuous variability, at least by inherent uncertainty. Yeah. So in that now, okay, I won't go to the whole scheme, but I made like a sort of inventory about which uncertainties have the highest potential for being reduced by doing measurements and by taking these two sources. So first of all, like what is the contribution to the total probability of failure? And second of all, do we expect that the uncertainty in this variable mainly consists of like the spatial variability, in which case we can reduce it? Well, again, this like especially for this anomalies and for the permeability and the D70, there's both like a high contribution to the probability of failure and like a high inherent uncertainty part. So it gives like, qualitatively said, it gives like a high potential for reducing that uncertainty by measurements. Well, if we go to leakage length, like the length of the seepage spot, that's like it also has like a medium contribution to the probability of failure, but the uncertainty in the estimate of the leakage length is hardly reducible by doing measurements. So the total qualitative effect of this is zero, of low. Sorry. Yeah. So based on this inventory, now this says you that like anomalies, permeability and grain size are the main parameters to focus on when you want to do measurements to well, potentially reduce the probability of failure. Okay, so that's about the uncertainties. Then it's about what kind of measures can we take in case we have like an unacceptable situation. So in case we have a probability of failure that's considered too high, higher than a certain standard. Yeah, well, there's many things we can actually do, but I consider here mainly like you can do structural improvements, like placing a berm to the dike, or you do measurements, right? Other methods would be like an observational method, like model improvements, etc. But well, we describe in the paper that it's considered to be less effective, so I'm not going to discuss this in this presentation. So if we have the trade-off between structural improvements and doing measurements, then we can make a decision framework to assess which is the most effective of the solutions. Do I have some?
2 minutes.
2 minutes. It will be fine. There's 2 more sheets, I think. So basically, if you do structural improvements immediately for your whole stretch of dike that is like considered unacceptable, then you have to make your cost of the improvements. If you do measurements, you have basically 2 options. Either you measure like a weak spot, and then you have to improve it, or you don't measure a weak spot, in which case you only have the cost of your measurement, right? So it's a very simple scheme, but it works well for evaluating, I think, the options you have. So if we start with one reach of dike as an example, we start with one reach of dike of 250 meter. We say that if we do one measurement in this dike reach, then all the uncertainty is gone concerning the parameter, in this case D70, which is of course quite a, well, not really representative statement, but for this example. And we only consider like discrete probabilities of D70, which says that it's either unacceptable or acceptable given a certain outcome. So now we apply the scheme on the previous slide. What we see is like, if you do like just immediately go to structural improvement, it costs you 250,000 euros, which you lose anyway. If you start to measure, what may happen? Well, you may encounter like a low D70 with like a probability of 0.25, which leads to an unacceptable situation. And so you still have to improve, so you have more cost there, like 280,000 euros. But if you multiply like the probability and the consequence, you get like the expected risk. Well, you can do that for all scenarios, that you measure like a mean D70 or a high D70, in which case, both cases, the probability of failure is acceptable. As well, we can add up the expected risks of all these 3 scenarios and come up with the total. Well, what you see here is like the cost of measurement, the cost of immediate improvement is much higher than the cost of measuring and improvement when necessary. Now we go to this length effector. So what happens if we have a dike reach which is like 1,000 meters long? We have like 4 sections. Now a few things can happen. You can measure either 1, 2, 3, or 4 weak sections. I assume I have to round up, I think, or okay. But anyway, so either of the scenarios, either number of found sub-breaches has an associated probability, a consequence, and there's an expected risk. And in this case, also the measurement strategy is way more profitable than immediately start to improvement. Well, basically, okay, what it says in these examples, the measurements are way more cost effective than the immediately structural improvements. You would clearly expect that. However, so first, when you start with this 1,000 meter dike, you have like an uncertain strength. If you start to do the measurements, you transform this uncertain strength into known weak spots. It doesn't mean that you don't have to do any structural improvement at all. It's only that your structural improvements are focused at the weak spots that you encountered. Yeah. Oh, sure. Well, this effectiveness of these measurements, it depends on the correlation distances of the parameters involved in relation to the measurement density, on the cost of the measurements and the reinforcements, of the contribution of the variable to the total probability of failure, and to the contribution of like the inherent uncertainty to the total uncertainty, as we discussed before. So I only showed a few examples here. If we elaborate on more examples, the most effectiveness potentially is in this exclusion of anomalies, in the measurement of permeability, and a bit less in the measurement of this D70 values to reduce like unacceptable piping situations.
Also, I thank you very much for your presentation, which is also very important, especially this 2D effect. There are not so many structures which are so sensitive to this problem. Risk associated with is extremely high. Therefore, we have to try to solve this question. And you was speaking about the weakest place, because we can have for 10 kilometers 99.9% safe or conservative. Only rest is not enough, and all the structure is in fact out of order, not fulfilling the main aim, and so on.
Exactly, yeah.
Please, question from the floor.
Wim, I'm Meijnerd from Deltares. I have a question about your liquid length. You have said that uncertainties are small because you can measure it. But what if there is a clay blanket on your river and you don't know where your infiltration point is? Or what about your geology? So the layers can vary, the height, the width, etc. Is that not a large uncertainty?
Yes, I fully agree with you. I have to tell with this example, we had relatively easy dikes. It was from a dike ring in the Netherlands where the entrance point was relatively well known. It was well known. It was just there was a sand layer just coming next to the dike, and also the exit point was focused by a small ditch. So then there was really small uncertainty in this leakage length anyway, because you really knew well. It gets indeed different when you deal with situations where you have like a really uncertain entrance point. Yes.
Thank you. Another?
All the dike sections that you assumed were statistically independent?
I assumed they were statistically homogeneous. Yeah. So they are the strengths of the resistance parameters are independent. The load parameters are fully correlated on the other hand. So they are partially correlated by that sense.
I assume if you do a measurement and you say at one point it should fail, and then you can assume that if you do a measurement at the next section, you'll kind of find a similar value.
Yeah, it completely depends on the correlation distance of the parameter you're talking about. So if you have like really short correlation distances, which might be the case for D70, might be even like 10 meters or so, I don't know.
I believe that there are many similar problems, questions. We can discuss it during the coffee break.
Yeah, okay.
Time is running very quickly, so I am asking the next lecturer, Daniel Bachmann from Institute